Hello, my name is Macoumba, PhD student at Sidi Mohammed bin Abdullah University in Fez, Morocco. I present our paper entitled Energy Efficiency Optimization Techniques for 5G Cellular Networks. This paper was co-written with Professor Balboul Younes from Sidi Mohammed bin Abdullah University, Professor Fattah Mohammed from Moulhime University in Meknes, Morocco, Professor Mazer Said from Sidi Mohammed bin Abdullah University, Professor Bekkali Moulhime from Sidi Mohammed bin Abdullah University, and Professor Kora Ahmed from Cheikh Anta Diop University in Dakar, Senegal. Our paper mainly revolves around 3 points. In the first, we dealt with the ecological challenge of this fifth generation. In the second, we detail the different strategy for optimizing energy efficiency in this fifth generation. And finally, we make a comparative study of these strategies. Ecological challenge of 5G. In order to meet the requirements of 5G in terms of speed, data, number of users, operator will have to further densify their network. This will have a significant impact on the environment on several levels. First, the overall energy consumption of networks, which is a direct consequence of the densification of networks and users. We can notice that 3% of the world's energy is consumed by ICT, which is also responsible for 2% of global CO2 emissions. The major contributor to ACT remains mobile networks. Second, the materials needed to manufacture mobile terminals and other network equipment. The manufacture of a smartphone releases 30 kilograms of CO2. In 2021, more than 1.5 billion of smartphones were produced during the year. This led to an overall estimated of 42 million tons of CO2 emitted globally. The extraction of specific metals and minerals necessary for production leads to dramatic changes in ecosystems due to toxic releases into the environment. The third point is the changes in use induced by their new performance. We will have more users, more volumes, more systems used. This is what is called a rebound effect, further accentuating this problem of energy consumption. All this makes the ecological questions a major issue in this fifth generation. Energy efficiency optimization strategies. Faced with this major problem of ecology in this generation, several strategies for optimizing energy efficiency have been proposed. These different strategies can be grouped into three. First, we have the strategies based on base station. Second, we have the strategies based on the organization of the network. And finally, strategies based on machine learning. Base station energy efficiency. The analysis of energy consumption within mobile networks has shown that stations are the entity that consumes most of the energy. They consume about 57% of the energy of the network. A large part of the research has thus focused on the energy optimization of the base station. Among the strategies explored, we find first, the C-RAN, which describes both the centralized RAN and the cloud RAN. The first describes the possibility of centralizing the baseband unit of the base station of a given area on a single site, while the cloud RAN goes further by virtualizing certain network function at the level of a server. Second, self-slipping, a strategy that aims to slip small cell based on cell load, cell selection, or traffic modeling. This is referred to an one-off switching strategy. Third, RRC connection control. which mainly impact the mobile whose permanent signaling exchanging with the base station promote faster battery depletion. And proactive data caching, based on data popularity, has also been proposed for small cells. Within the network, a significant part of the load corresponds to the same request or similar content. There may also be specificities depending on the area or location. Strategies based on network organization. Among these strategies, we have those based on resource sharing, on NOMA, on the use of unlicensed band for indoor use, or virtualization. Several studies have been made on improving energy efficiency based on the sharing of physical and spectral resources between operators by sharing infrastructures, with a gain of up to 55% in dense areas with less interference. Proposals have also been made to use NOMA associated with power control to improve energy efficiency and also to serve a maximum of users in the same frequency band. The use of unlicensed system or bands for indoor use have been mentioned in several studies. Last, the virtualization of certain networks function, which previously were on dedicated hardware, is increasingly explored line of research. Machine learning. It is increasingly present in ICTs. It is used in 5G network to optimize several metrics, including energy efficiency. A typical case of use of machine learning is a smart antenna, which can, for example, adjust its power or its frequency band according to the learning from the signals received. We also find small cell activation or deactivation policies to optimize energy consumption through distributed learning applied to incoming traffic requests. We also find automatic learning techniques for energy efficiency resource allocation. And also we find spectrum detection techniques based on mathematical analysis in order to reduce the interference problems accentuated by the random deployment of small cells. Comparative study of strategies. Finally, we made a comparative study of these different groups of strategies. This comparison was made at three levels: the complexity, the gain, and the cost. We have this table which presents the result of this comparative study. Consuming nearly 60% of the energy of the network, the stations naturally present a major interest in the quest to improve the energy efficiency of the network. They concentrate the greatest diversity of strategies. Some areas are, however, increasingly explored, such as C-RAN or virtualization, which occupy an important place in the definition of future technologies. So, in terms of complexity, the application of certain strategy will prove to be much more complex than others, both at the structural level and at the technological level. Taking the example of the sharing of resources and infrastructures between the different operators, despite a gain of up to 55%, this seems delicate from a regulatory and economic point of view, the operators being until then mainly private with own investments and management. The strategies applied to base station based on machine learning seems to be of less complexity and are more integrated into the implementation schemes. In terms of gain, the on-off switching strategy make it possible to be at an interesting level of improvement in energy efficiency, always because the base station is the most energy consuming entity in the networks. The Sharon wish the centralization of baseband unit allow a real reduction in consumption. The reduction of interference certainly allow a reduction in transmission power and therefore consumption, but not in the same way as on-off switching. However, it has a very positive impact on throughput, which makes it a very important strategy for future 5G deployments. Regarding the cost, the various strategies for improving the efficiency of consumption require a more or less significant cost depending on whether or not they involve a review of the infrastructure, equipment, components, connection, etc. or not. The strategies applied to base station have a moderately low cost, requiring little integration of new component at the base station level, except for the CRAN, which suggests a centralization of BBUs, baseband unit. Strategies based on virtualization can be expensive for an initial deployment. However, on systems already in place, their implementation remains very inexpensive because they are more using software than hardware. In conclusion, we can say that this group of strategies, far from being concurrent, can be considered as complementary and must will be an integral part of the next 5G deployment or even future technologies. In order to more effectively achieve the ecological objectives of 5G, all these aspects should be taken in account in order to define this so-called breakthrough technology in long terms. Thank you.